Up until now, we've been discussing basically this from a theoretical point of view. We've done some examples and how it works. And when I say theoretical, I don't mean it in a sense of its pure theory. There are also, as we've seen, practical ways of dealing with these problems. And you should be at this stage able to answer most of them. And we'll do some in a little bit later as we sort of fill out more and more of the coursework. Now, essentially what I want to do in this lecture is I want to deal with the issue of graphs. Now, as you all by now are well aware, most of the stuff in maths, in physics and chemistry, we kind of love graphs, okay? As scientists, engineers, which are the applied versions, I guess, the theoretical scientists, graphs play a big role. Why? Because they're a picture. It's a snapshot of events, okay? We can plot graphs quite easily from data. Data itself is pretty, I don't know, it's boring because it doesn't say anything until you actually see it as a picture. Well, that's me anyway. Graphs, I want to get my title right. Graphs of changes to equilibrium conditions. Okay? Now, what do I mean by that? I mean that we are going to look at a graph which is over time, and we get to an equilibrium, then we make changes. We're going to look at what happens when we change pressure, catalysts, temperature, etc. We're going to look at it graphically. We've seen it theoretically in the examples we've done. We're now going to look at it graphically. Now, before we start, I've always said, and you've probably heard me say it many, many times, when you're looking at a graph, you're given one, the first thing you do is what? You check the axes given. Okay? Now, in these, you will always find time, okay, as the x-axis like that. Okay, this will always be time, and there are two separate graphs here that you have to know. Okay, the first graph, okay, is where we've got concentration. We could have concentration. I'm going to do that. We could have could be given moles per cubic decimeter. We could have moles. Okay, we could be given mass over here, mass of gas or mass of whatever. We could be given a set of measurable variables down that side. These are all issues here that in fact we know how to deal with by going back to the actual equation, the chemical equation balanced of the actual thing itself. Then the next one, which is slightly more difficult, rate of reaction. Okay, now first, let me just go back to the beginning of where we started this whole process. We started it here, where we said the rate of reaction, okay, and the others, okay, at t equal 0. And please, the same as with the endo-exo graphs, label it reactant, product. Label these as reactant and product. It is a huge help, because the logic flows through and you can see which one has then been actually changed, and you can work out what happened based upon knowing what was changed. Okay. So now we say okie dokie. Remember we said in the beginning, I'm going to do first of all over here the rate of reaction. The rate of reaction. Well, at time equals 0, how much product did I have? Okay, I had reactant. I had all reactants, and at time 0, I had no product. All right? Obviously, the rate of reaction could be whatever per unit time. All right? So it's essentially the other axis divided by per unit time. Right, so it could be moles per unit time, change in constant, whatever. But it's per unit time. Okay. Now, on this one here, what we said is this graph came down like that, And then I said that this graph went, let me just do it in blue. I can't remember what color I did it in, but I said that this graph, okay. Now let us stop and let us look at these two lines. This essentially over here means what? It means that the rate of reaction, this is reactant. And the blue one is product, isn't it? The blue is product. It means that the rate, it means I am using reactant up at the same rate as I am, where's my, sorry, I want blue, as I am making product. Okay, does that make sense? I've got all reactant at the beginning, and we said it goes quite steeply down, and then it equals off. So this here could be, for example, 3 moles per minute. And the one underneath would also be 3 moles per minute. Okay? In other words, I'm using up reactant, okay? All right? And product, okay, is the same in effect at equilibrium. So the making of the product is actually the reverse reaction, if you think about it, isn't it? Okay? I had no product, I make product. Now at this place here, I am making and breaking at the same rate. Okay? So let's just get that through. So we say, right, the one is I had no product and I made product, and then now my product and in other words, my rate of making product is the rate of making reactants. Okay? That's what this rate means. And at this point here, what this means here, we said at this point we are in equilibrium. Okay? Okay? So I'm using up my reactants and I'm actually breaking product, if you like. I know I've got making product. All right? I had no product, I make product, I get to there. But just think ahead, what we've got is at that point, the makeup and the breakup. Let's look at it from that perspective, shall we? Okay. So now let's just start off and analyze at the beginning at t equals 0. Okay. As I start, the rate of reaction is 0. It hasn't happened. Then I start, time marches forward. I have got a forward reaction which is high. I am actually using up, okay, at 10 moles per minute. And my reaction rate here is small, all right? Reverse reaction. Why? Well, the reverse reaction is the breakup, isn't it? The breakup is the reverse reaction. So in the beginning, I haven't got many ammonia. Let's take ammonia. Or let's take our steam. I haven't got many steam molecules. So I'm making them fast. But at some point, my steam molecules start to condense. And then I get to an equilibrium situation. So as time marches on, my rate of reaction forward drops to 8. Okay, this might now be 2. These numbers mean nothing. Okay, this is after t equals to 2, let's say. Then we say, okay, at t equals to, let's say 5, my rate forward is going to be 3, and my rate reverse is going to be 3. All right? Makes sense? So what we're saying here is we're saying the forward reaction and the reverse reaction, let us say at t equals 5 minutes, come to 3 and 3 in reverse. Because now the forward is making product and the reverse is breaking product. All right? Forward and reverse reactions. So over time, we notice that the rate of reaction actually joins together. All right? Now, if I change something, all right? If I change something, I can either, remember, we are here now. We are equal. Let me make it bigger, okay? We are equal, right? That's not going to work. We are equal. Tell you what, let's make that, let us make this one a blue one. All right? Let's say there we are. Okay, so this is reverse. Okay, rate of reverse. Okay, this is the breaking. The breaking up. And the top one is the forward, okay, is the making of product, right? Breaking up of product and making up of product. Now I do something. My something can have a few options. First of all, there's my current level, all right? And now I make the forward reaction, I increase it. I increase the forward reaction. Well, currently, where am I? That's here, all right? Now, if I increase the forward reaction, we need to know what's going to happen. So when we do this and we're going to get to these, we ask how? What did we do to increase that forward reaction? So basically what we're saying is we're going to start studying those. Before we get to that, there are some easier... I do wish that it wouldn't do that to me. It's terribly... Hey, anyway. All right, I think you guys have got the gist of that. So what we're saying here is we are saying, come on, blue, okay? We're saying that we're going to study those. Before we get to those, let us look at the other graphs. Let us look at the graphs, the straightforward graphs, which are where I'm measuring graphs of here, over here, for example, concentration, mass, moles, etc. There's many things that we can measure down here, right? That arrow could confuse. It doesn't mean it's going up or down, all right? And here, this is going to be time. Ooh, come on. This is going to be time, all right? Now, when we do these, it's different. The graphs do not come together. I am going to start with product. Now, I start with product just A and it goes to B. But product A can come like this, okay? Whereas product B can do this, okay? This is product. This is now reactant. Yes, we can say that at this point here, all right, let's say over there, this is time to reach equilibrium is over there, and this is T0 always. So at T0, let's just recap. At T0, I have all reactant. No product. Okay? Blue, no product. Zero product at the beginning. After a while, now please note, I'm going to do it in red. NB. Look at what we are reading off here. We're reading a concentration or a mass or moles. Okay? Which means what? Which means the number of moles. Let's talk about the number of moles. Or the whatever. The number of moles has dropped. Which means that at this point here, I still have reactant available. Okay? I still have reactant available and my product is constant. Okay? There's still reactant available. It's not zero. Because these reactions are not necessarily to completion. I haven't used up everything necessarily. Okay? Because equilibrium remember what we said in the boiling kettle, I'm going to keep going through that loop for a long time until I change something. So I say over here, I say, okay, that is now, I've got product, it's a mass or a moles, it's a concentration, not a rate. And at the bottom, I have still got reactant left. So you'll see products like that. You will even see graphs that look like this. You'll see this, for example. Just let me draw one. And this has no particular meaning. I'm drawing it for illustrative purposes. All right. And you will see, say, for example, let's do this. Red, say we had that. This one might have dropped to there. And you'll see product, okay, maybe like that. And you will see another one, the blue one, maybe doing this. Okay. That doesn't mean that they're in equilibrium in a rate. It's not a rate. Equilibrium occurred over here at, let's say, that point there. Okay? T till equilibrium, because that's time. So the first thing we go and we say you are a reactant. Let's call you reactant A. The red one is reactant B, and I'm labeling them, look. Reactant B. The other one, the green, is product C. The blue, okay, is product D. Reactant A, reactant B. Because I've got two reactants to give me two products. Okay? Now, that means I could be doing, let me say I've got concentration here. It means the concentration of A has dropped and the concentration of B has dropped. But they've dropped differently. Why? Because of the mole ratio. Let us just take a simple one. Let's go back to our N2H2. N2 plus 3H2 goes to 2NH3. Remember that? Look. Every 1 mole of this reacts with 3 moles of that. So if nitrogen was the top one, the bottom one, okay, reactant B, is going to be the hydrogen. Because the hydrogen is reacting, more of it's being used up. Right? So if you're going to do this, all right, you obviously would start more or less with 3 times the amount of nitrogen. Because you know, for every cup of nitrogen, you're going to take 3 of the same. You're going to take 3 cups of hydrogen. So you want at least to make sure you've got enough. Otherwise, one of them, if it goes to 0, is a limiting reactant, limiting reagent. Our task, thus, is now to say we are at equilibrium and we understand that. Okay? We understand that condition, that we are there. Now we're going to start changing reaction or changing equilibrium conditions. Right? So now let us change equilibrium conditions. Let us change the equilibrium conditions. What do I mean? I mean that I am going to take a graph, all right, like this with time, and up here, something, concentration, etc. I'm just going to write that. Some measurable, not rate. Rate is something different. So that is where we're going to start. And I'm only going to use two, okay. I'm going to say that, and I'm then going to say this. Color do you want? Blue. Let's use blue. All right, and let's say we get something like that. All right. Now we say, okie dokie, time to equilibrium. We look where these graphs are, let's say there. That is time to equilibrium. We've reached it. Now I am going to change pressure. Change pressure. Okay? Now, if this is in concentration, look here, concentration is moles per decimeter cubed. if I change pressure up, volume goes down, doesn't it? Which means there's a change in the concentration straight away, because I'm measuring concentration over here. So you have to look here at what is being measured. Generally, I think they're going to give you concentration ones, all right? But just look if it's mass or if it's moles of stuff, all right? Because then the graph is going to be different, all right? Let me see. All right, now if I suddenly, let's say I notice that at this point over here, all right, at this point I indicate a change, and the blue line does this, and the green line does, the black line does this. Okay, whoops. Okay, I need to just, sorry, don't put that one in yet. I notice that there's a change. I need to see what did I change at, let us say, I don't know, at t equals, say, 10 minutes, they ask me. I go along and I say, what did it look like? Now remember, when I change the volume or the pressure, if I increase pressure, what is going to happen? Both of these are going to go up immediately. Aren't they? Right? And blue. Both of them will go up immediately because my volume has changed. I have increased the pressure or decreased the pressure. I am changing the volume, which means the concentration must be changed. Does it not? Now, when I do that, okay, the pressure increases. Okay. Now, let's say that this we don't know what this is at this point. Okay. We don't know what it is. All I tell you is that this is what happens. Okay. The blue goes like this. All right. And the black one does this. Okay? Right. So straight away, if both are affected, I have changed pressure. All right? The change in pressure that I did, all right, affected both immediately because it changed the volume, and I'm measuring it with volume. And there's my volume there. All right. So if I put the pressure up, volume goes down, those would go up. So in this case, I probably increased the pressure, didn't I? So what did it favor? Well, let's just fill in. The blue over here was my product. You'll see why you need to fill them in. So what did I do? I increased product, right? I increased product by this change in pressure, all right? I increased product, which means I must have decreased. And I decreased, which means I used that, which means I favored the forward reaction. Increased product, making product means it's going that way. So if I make product, I favor the forward reaction. Okay, these are not absolutely simple that you can just rip through. All we said is we increased, okay, the pressure here, because what did I do? My volume went down. Okay, if the volume goes down, let's just look at it arithmetically. Let's say my moles was 5 and my volume was 10. Therefore, that ratio was a half. Now, my volume has dropped, okay, to 5. The ratio has gone to 1. So therefore, okay, my has increased. Okay. Now, I say okie dokie then. I have favored the forward reaction. We don't know what the reaction is. You don't need to know. All you know is you favored the forward reaction. Okay. If it was ammonia, okay, you increase the pressure it would move to the low side, which means you would favor that. Remember, the ammonia one was N2 plus 3H2 reversible going to 2NH3. And we said there's 4 moles here and 2 moles that. We identified high pressure, low pressure. If I increase here, it'll favor the forward. Right? I favor the forward, so this is kind of an ammonia one. All right? If I decrease pressure, what is going to happen? Well, let's just draw it. Okay? We know it's the ammonia one, so let's just draw it. Let's say we are here. All right? And I've got this guy here now. And we've got, what did I use? What color did I use? Let's see, I used blue. So let's use blue again. Okay, so there we are. And let's say that's time at equilibrium. And the change I made was at this point here. Let me just go to green. I made my change here. And in this case, I went, let's put you back on. Okay. Black. This is product. Blue is reactant. Right? Now, let's see what the graph would do if we know it's ammonia. If we change pressure, if we reduce pressure, we are going to go the opposite way, which means mine is going to, oh, it's the wrong color, isn't it? Black, it's going to fall. But both will fall, correct? Because I reduce pressure. Then what's going to happen is if I reduce, I favor the other way. So my reactant, okay, sorry, oh, Kevin, why didn't you guys tell me that I had it the wrong way around? This is my, no, that's not what I want to do. I want to erase you and you. See, get myself confused here. Black is the reactant, blue is the product. But if you logic them out, you'll be able to correct that. Okay? So I've dropped it. So it means I'm going to start using up product now, aren't I? My product is actually going to drop. And my reactant is going to increase. Like so. And yes, I get to a new equilibrium. New equilibrium over there at that point. So that is the graph of a pressure change. If I go changing it, it means that, all right, I'm going to do that. Now, you don't need to be given the reactions to see what happens. If you are given the reactions, you can work it out from the theory side and confirm it with this. Okay. The key there is to remember that both of them go up or both of them go down, depending on what you're going to do. And then the reaction will tell you. So it will tell you automatically which is the high and which is the low pressure. What do? I look what the change was. The change was over here a pressure reduction. It could have gone the other way if it was a different reaction, couldn't it? It could have looked like this. Now this is a different reaction, guys. It is not ammonia. Okay? It is something else. It's a reaction A plus 2B goes to 4C. So this is 3 and that's 4. This is high and low. So if I increase there, I'm going to favor that way, aren't I? So in that case, from equilibrium, all right, we would have we've reached equilibrium, and I'm only using, let me just use blue. I'm only using 2 lines. Let's say A and B reacting the same. All right? I label them and I say you are product. And you're not going to catch me on that one again. And you are reactant. We're at equilibrium. There we go. Now, I say okie dokie. I make a change at equilibrium. Over there, I change it. Okay? Let us say that in this case, I increase the pressure. Right? So pressure increased on both of them. Right? I note that both increase at the same all of a sudden. What is going to happen? Well, in this case, it's going to favor the opposite. It's going to favor the reverse reaction. So increase pressure favors reverse reaction, which means I go that way. Which means what? It means my reactant is going to go up and my product is going to fall. But my reactant goes up black. My reactant goes up like that. Okay? Because I'm making a reactant and I'm using up product to do it. And then I get you a new equilibrium. And very often in the examples that you see, you will see written on here a number. Say 0.5, 0.3, and this goes to 0.6, and that drops to 0.25 over there. Those are numbers that tell you what the concentrations were at that point. And that allows us to calculate something into the future. So that is changing pressure, okay? Because it affects both sides equally. Once you increase the pressure, it affects your reactants in the tank and your, your products in the tank as well. So that's cool. The next one we're going to do, okay, is we're going to look at a, I've got that. I'll just go through something to do with the P1, V1, pressure again, and then we're going to look at something to look at, yeah, that one is, oh well, we're going to look at, let's look at concentrations and things like that, okay. We're going to change it and look at some rates, all right. We will return and we shall continue. Keep well. Have a good one. Bye.